All right, for those of y'all starting the video at home, there are a folder with 3 videos just above this one in Schoology that are what I just showed to the class. So watch those 3 videos. A question that I was just asked was, got it, thanks.
Yes, I'm ready for it.
A question I was just asked had to do with what is an elaboration on cohesion. So the answer is that cohesion was yesterday. Cohesion are the intermolecular forces, all right? Because cohesion is going to be what holds a substance together, but not bonding it together, which is everything we covered yesterday, where adhesion is going to be that substance being attracted to a solid surface. Other questions on the videos you just watched?
Wait, can you repeat the adhesion part?
Adhesion is going to be the attraction between a liquid and a solid surface.
Would blood react the same way like milk in that video? Like if it dropped in like that?
Yes. Okay, so if you could help me out, person. And so here we go, person. So this first slide really just matches what you saw in the video just now. However, the video did not cover viscosity. So just a quick reminder, I demoed this idea last year in pre-AP, but for you to see it one more time, viscosity is the resistance of a fluid to flow, meaning the slower something flows, the slower the liquid flows, then the more viscous it is. So if we race these guys together, all right, gray in my left hand, red in my right hand, going by the tube colors. All right, if I flip them, you will see bubbles race one another. And whoever loses would be flowing more slowly and would therefore be more viscous.
What are the substances?
I used to have a one with glitter just like that.
So which one is more viscous?
The gray one.
The gray tube, because he moved slower. Now, here's an idea to add to viscosity, though, that I'd like you to know just in case an FRQ gets fancy. Usually items that contain sugar tend to be more viscous. Sugar is a large molecule, and if you're made up, comprised of larger molecules, it's usually going to add to, well, the thickness of your structure. So liquids with sugar tend to be more viscous. And so hopefully things like honey and molasses just came to your mind, which kind of feel like pure sugar. What's that?
I like drinking jam.
Gabriella. I knew your name there. Okay. Also, it went over meniscuses with you, and this is absolutely something that you'll want to know the difference between. Also, make sure you know what convex and concave means. All right, concave means that it is caving in. All right, you don't want the ceiling to concave on you. But just keep in mind that if it's a polar solid and a polar liquid, then the liquid loves the solid, because like dissolves like is the phrase that should live in your brain. So it's going to make the liquid want to go and, well, love on that solid. So what does it do? It creeps up the side of it, which is what makes that dip. But if you put something non-polar near something polar, well, then they hate each other, all right? It's the Jakob Effect. Just kidding.
I read your books.
You did. Which is going to, if you look at the shape of Mercury, really you should think back to that circular shape that the video first described water in, whenever it is just being cohesive. Well, that's when the particles are loving themselves. Because if the mercury is in that glass tube and it hates the glass, then the mercury just wants to be by the mercury. And being in a circular shape is going to help promote that idea, which is why it's got that curved top.
So for the picture, does it matter like just two?
Well, it matters what the test tube is made of, but glass is polar, and it's usually all glass. So, all right. So then let's move into new stuff. Oh.
It's like water. What is glass? Glass tastes like water.
All right. The bulk of this lecture and what AP wants you to know are the 5 types of solids and characteristics of them. The good news about this isn't only one of the 5 is something that's probably brand new to you. The other 4 are not. The other 4 are stuff that we've been talking about all year long, but now we just need to make sure that we know their descriptions, which again still shouldn't really be too new to you. So really the way that I see these 5 that you're required to know is another memorization assignment, but less intensive, less intense than the Vesper was. So let's start off with crystals. All right, you already know what a crystal is. You already know how to identify a compound as ionic, right? A metal with a nonmetal, all right? Or a polyatomic bonded to anything is going to have my crystal structure. But once you know it's a crystal structure, there's items that you need to know. Things such as, Alyssa, you're doing that thing that you do. Are my slides on your phone right now? And he lies. So, ionic crystals are going to have a high melting point, all right, and a high boiling point. So what that means is if I take something that you know is ionic, like table salt, and I put it on a hot plate and I pump it up, it doesn't melt. You can get it to melt, but the salt will just get really hot. It's hard to get it to melt because ionic crystals have a really high melting point and boiling point. They do dissolve in water, and they conduct electricity. If you think back to the electrolyte lab from last year, remember when we made the light bulbs glow? Yes. Anytime we had an ionic compound dissolved, it made the light bulb glow really bright because they're considered electrolytic. So ionic compounds do conduct electricity in solution, but not when they're solid. All right. If you take that solid salt and try to run a circuit through it, it won't conduct. Alyssa.
What if it was like rock salt? Is it the same thing?
Yeah. Yeah. I'm just using table salt as an example because you're familiar with it. This applies to all ionic crystals. What?
It smells like crystal meth.
Really?
Yeah, what's up?
I'm recording, so I'm not even going to be funny.
It's educational. We're not talking about crystal meth.
You were gonna kill
He
us.
said this was the boring.
Yeah, but you forgot which video that was.
No, I didn't. Black tar heroin makes
So then if one type of solid is ionic, then it would make sense that a second type would just be covalent. But underneath this slide, please write the phrase molecular. I shouldn't have to say that, but I think some of you benefit by seeing that word connected to covalent as often as possible, because they will use them interchangeably. All right? So a covalent compound, a covalent solid is the same thing as a molecular solid, which, Isaac, it's 2 nonmetals bonded together.
That's what I figured. I just want to make sure.
Covalent compounds have a far lower melting point, which means if I go back to the hot plate that had the salt sitting on it and I put a pile of sugar next to it, the sugar melts fast. The sugar will just go black. All right, smells amazing. All right, while the salt again is sitting there not melting because those covalent structures are easy to melt. Now we have to remember though that my covalents, my moleculars do not conduct electricity. Again, if we think about the electrolyte lab, the sugar water or anything else that was covalent did not make the light bulb turn on.
The only time I actually saw sugar water in real life was when I would have said.
So then let's move into the one of the 5 that is probably brand new to you, and it's called network covalent. Network covalent is interesting because it's super, super specific. There are only 2 elements that you are going to look for in order to classify a solid as network covalent. One of them is carbon, all right? if carbon is bonding to himself, he can do it in an amazing amount of ways. We call these allotropes.
Oh.
Carbon bonded to carbon in different ways that actually form different substances. Can anybody name some carbon allotropes? Diamond, our favorite one is diamond. What else? Graphite. All right.
Ruby.
All right. Not
Emerald.
charcoal.
That's what
All right. All of those things are comprised solely of carbon. No, solely of carbon. All right. Oil and humans have other things in them. All right.
What about aspartame?
Now, the other element to really focus on is silicon.
Yes.
In this class, if you have a bonded silicon in a solid phase, it's automatically network covalent. Anytime silicon is bonded in the solid phase, you will automatically classify it as network covalent, and it will have these other attributes. Yes?
So it has to be bonded to each other. There can't be anything else in it. There can't be any
If it's the carbon, it's going to be pure carbon. All right? If it's silicon, it's going to be silicon bonded to something else.
So are those the only two things?
Those are the only two.
carbon, like
That's it.
an infinite amount of carbon, like 20, would that work?
Yeah, you can go up to, remember the article that you read used C60.
Oh, the bocce
Bucky balls.
Bocce balls.
Bocce balls. Italian bowling, I remember. Anyway. So just to elaborate a bit on the allotropes of carbon, this shows you diamond and graphite, but I like to talk about graphite a little bit because of how often y'all interact with it. Most of your pencils use graphite, and I just want to talk briefly about the carbon structure there. If I have a bunch of carbons bonded together to build graphite, what type of IMFs are making that attraction possible?
London dispersion.
London dispersion, all right, because it's going to be carbon with carbon, therefore nonpolar. Isaac, I'm struggling to overcome your chattiness. Can you please do me a favor?
Yeah, no, my bad.
I appreciate it. That means that it's actually a weak attraction then, right? Those London dispersion. So when you have your pencil that's got these graphite layers, the moment you push it against the paper, all you're doing is overcoming the IMFs. You're breaking the London dispersion. So what does the graphite do?
Right.
It writes onto the paper into your terrible handwriting.
Okay. I have an actual question. So, in the past, I was stabbed with a pencil by a classmate, and it's still in my arm.
Mine too. I have it in my thumb.
Yeah, mine's somewhere in my arm.
Where is the fun?
Yeah, here it is. It's right
Why is
there.
diamond the strongest? It has to do with the layer upon layer of carbon underneath an intense pressure to make it possible.
What's the other way to say it's done?
Not the strongest.
Like in a wedding ring, how much carbon
So,
is in a wedding ring?
I-
Average done.
So moving on to structure 4 of 5 is going to be my just metals, all right? If you've got a metal by himself, then we call it just a metallic solid, not bonded to anything else, just the singular metal. So if I take a singular metal, if we assume that this is silver, then there's some automatic attributes that I would know. But of all these attributes that I want you to know, the most important one is the phrase Sea of Electrons. We need to always associate the phrase Sea of Electrons with metallic bonding and solid metallics. Now, there's a secondary descriptor there that I also want you to know, having to do with the fact that the electrons are just moving away from the atoms that brought them there. It starts with a D. Does anybody know what word I'm thinking of?
Ductile. What are you saying?
a word that describes electrons' ability to swim away from the atoms that brought them there when they're in a metallic bond. I need you to write down the word delocalized.
Silly word too.
Okay, but real talk, Mr. Cummings, so I never really was taught what a sea of electrons is.
I'm about to show it to you.
Okay, cool.
All right. Delocalized is another real good AP word to help describe the Sea of Electrons. So what is the Sea of Electrons? Well, to show you again, you learned this last year.
I didn't.
But if I were to zoom in on that metal bar I was holding a moment ago, it would be comprised of a whole bunch of silver atoms. We know that all of these silver atoms that are metallically bonded to one another initially brought all of their own electrons to the equation or to the solid. So if I were to, and this is an oversimplification, but if I were to say, okay, well, here's the electrons that atom brought. So this is one silver atom in blue and 3 purple valence electrons that he brought along with them. What the Sea of Electrons says is that these electrons are delocalized. It means that they are not local. Like if I use the word local to you, you should think of, oh, well, San Antonio's local. All right, these guys aren't. All right, these guys go to the south side. All right, they are the ghetto electrons. I'm just kidding. But they are, I'm just kidding, I love the south side.
You would have
Please don't tell them I said that. Okay.
You're on
I'm from Puerto Rico.
This is about the problem of people that live with the south side. They're like,
So what is delocalization?
So, since they're delocalized, it states that these electrons are going to swim away from their home. Actually, all of the electrons that all these different atoms brought get to swim or move across the entire solid sample. They get to leave the atom that brought them there, so they delocalize, they're moving from their home, and they are welcome to travel throughout the entire solid. So it's 2 ways of saying the same thing. The Sea of Electrons, because they get to swim across the whole sample. Delocalized, because they get to leave their home atom. It's this Sea of Electrons that creates some of these other characteristics of metals that you're already used to, that you're already aware of. For example, if I apply heat to this part of the sample, or even more specifically to that electron that it's pointing to, what was that electron about to do right before he got zapped with heat? He was about to swim across the sample, which means if I am physically holding this sample right here, and that electron that got heated up swims over here, what am I going to feel? Heat, which is why metals are conductive, because all of those electrons are swimming around. So by giving this part of the sample a characteristic, well, it swims and delocalizes and gives all of the sample that characteristic.
Is that hard to hold? Is that like actual silver?
No, this is steel, I think. But
it.
I don't think it's very hard.
What did I call it here?
She didn't flinch. She knows I don't want to get fired today. Tomorrow's a different day, though. Okay.
No, she's pregnant.
The 5th type of solid that you need to know is lone atoms. And really, this is the only one left. If you look here real quick, I want you to understand. One of the solids is a metal with a non-metal. One of the solids is a non-metal with a non-metal. Right? One of the solids is the super special one, silicon and carbon. All right? And then we have a metal by himself, metallic. And then we have a non-metal by itself, lone atom. So really, these different samples are pretty much all of the different possible ways that elements on the periodic table can either combine with something or be by themselves. So a lone atom is going to be a non-metal that's just chilling, all right, but not carbon. All right, and then it's going to have these characteristics that you need to know. What's that? Silicon has to be bonded. So carbon, so for the network, it's a carbon by itself or a silicon that's bonded to build the network.
So it could be a silicon by itself?
Yes. What's that?
You both have to be in solid state. Like,
Yes, in order to, because everything we're talking about right now is solid.
No.
Now, there is an add-on idea, all right, which is alloys. All right, alloys is going to be a metal with a different metal. All right, a mixture of two metals, and they create a lot of substances that you're very familiar with. All right, but what I need you to know in AP about alloys is the two categories. We've got substitutional versus interstitial. All right. And they're real simple. You just want to have this vocab in your brain on AP day. But for it to be substitutional, as the picture shows in the slides, the normal arrangement of atoms, all right, it changes what metal is in that predicted arrangement. Remember, we're talking about solids, so the structure is very organized and predictable, right? In substitutional, it's just throughout that predicted pattern, it switches what metal is which. It's two different metals, and it just alternates. In interstitial, it doesn't do that. It's only one type of metal atom that's creating the pattern. But then there's a second type of atom that is filling in tiny holes in between the atoms. So they are distinctly different from one another.
This number's called me twice, and I can see what it is. It's like,
Yeah, step outside and do that. That'd be great. Cummings just going around there.
Quick, there's one.
What?
yeah.
Oh, dang, I'm not doing well. Okay, well, we're getting to the end. We'll do the last part all together. But as far as alloys go, usually the metals that you know exist but aren't on the table, those are alloys. Name some.
Titanium.
No, titanium's on the table.
I played Minecraft before mine.
Name metals that are not on the table. Steel.
Baby, let's go.
Babies. No. Brass. Bronze. Items that sound like they would be an element, but they're not. Copper's an element! Okay.
Lead.
All right, here we go. Focus, focus. I know we're near the end. So, can you classify them? If I give you a sample and I say, hey, if this is in its solid form, what is its classification? You've got to be able to do it. So, let's just go straight down here. I'm going to do the first one for you. Watch, watch, watch. Shh. O2 is an element by itself. So now I say, okay, it's an element by itself. Is it metal or non-metal? All right, it's non-metal. So if I have a non-metal by itself, what is it?
Lone atom.
It's a lone atom. Do you see how I did that? Let's see if you can do the same thing. Let's go over to cluster 1, seat 3. All right, so what do you think about H2S? Which of the 5?
Well, it's a non-metal with non-metal.
No, perfect. And she's doing it. A non-metal with a non-metal is molecular, right? It's a covalent solid. Perfect. Let's go to cluster 4, seat 4. Hey, 4. What do you think about AG? Lone atom has to be non-metal. That is by itself, but it's metal, so it would be... Quit helping. It would be metallic. Thank you. Let's go to cluster 3, seat 1. 3-1. That's Isaac. Aspen, you can do it. KCl. Covalent has to be a non-metal with a non-metal. KCl. Ionic, right? It's a crystal. It's a metal with a non-metal. Let's go to cluster 1, seat 3. Again, 1-3. What about SiO2? What? Nope. Nope. Hey, see silicon? Silicon's, ooh, that's a bonded silicon. Network covalent. Watch out for bonded silicons. All right. Let's go over to cluster 5, seat 5. That's Aspen again. I'm at you, Annalise. What about neon?
Repeat.
Neon.
Now, what's the question?
Say it again.
Uh-huh.
What type of solid is neon if he's solid?
Non-metal.
He is a nonmetal, so what does that lead us to?
Lone atom.
A lone atom, very good. Let's go to cluster 2, seat 6. Aspen again, can you do NH3 for me? It is molecular. Show me the next slide. The bell's going to interrupt me on this last part so y'all can watch it on the video. Another thing that they like to do though, as the last slide shows, is give these general descriptions of a compound where you have to dig into things like melting point and conductivity. So, if I look at the first one and I look at the fact that it's got really high melting and boiling points, right, and it can conduct electricity as both a solid and aqueous, that must be, anybody? Metallic. That must be metallic. Going to the second one on the last slide, all right, it looks like the boiling point and melting point have dropped significantly. All right, so on this one, and it doesn't conduct electricity in any state. As you look at those descriptions and compare it to the other ones, you'll see molecular. The second one is covalent molecular. Finally, the last one on the slide. All right, you'll notice that we're back up higher on the melting and boiling point. And look, it conducts electricity when it's in solution, but not when it's solid. Looking at that with the other characteristics, the last one would be ionic, an ionic crystal structure.
Okay, now that you're less stressed, can you explain that again?
Ionic.